Welcome to the titration calculation tutorial. In this tutorial, we're going to take a look at two different techniques for solving for the unknown concentration of substances in a titration problem. As with the previous tutorials, each problem will be introduced with some focus tips and then wrapped up with some thoughts and questions for you to consider. In this first titration problem, we're going to use both techniques. As you're going through this problem, I want you to focus on these two techniques and consider which one you feel more comfortable with. Which one do you think will work better for you when you're solving these problems on your own? The two types of ways you can solve each problem are going to be stoichiometry or using a special equation that comes from the dilution equation, M1V1 equals M2V2.
During a titration, 30 milliliters of 0.500 molar HCl neutralizes 45 milliliters of KOH. Calculate the molarity of the KOH. In this problem, the first thing you want to do is identify what is the titrant and what is the analyte. The titrant is the thing that has a known concentration. The analyte is the thing that has an unknown concentration. Therefore, in this problem, HCl is the titrant and KOH is the analyte. As with all titration problems, the next thing we want to do is identify and balance the neutralization equation for this titration. Here we have that HCl plus KOH yields KCl and H2O. Which of the two products is the salt? You can think about that and answer it on your own. We can see from the balanced equation that there's a coefficient of 1 in front of each of the substances. It's a very easy equation to balance. Well, we need the balanced equation so that we can do the stoichiometry. In this process, we start with the concentration of the titrant, the thing that we know the concentration of. So, we have 30 milliliters of HCl over 1. We need to convert those milliliters into liters, using 1,000 milliliters for every liter in the next fraction. From there, we take the molarity of the HCl and convert it to a fraction of 0.500 moles of HCl over 1 liter of HCl. This will convert the milliliter amount to the liter amount to the mole amount of HCl. Next, we take the mole ratio, 1 mole of HCl to 1 mole of KOH, and we divide those to get our final answer that the moles of KOH is equal to 0.0150 moles of KOH. Keep in mind that the mole ratio of 1 mole of KOH to 1 mole of HCl comes from the balanced equation. The coefficients are 1 and 1. Of course, dividing and multiplying by 1 mole over 1 mole doesn't change the mathematical answer. It just makes sure that the units cancel out correctly so that we're left with moles of KOH. Well, we need to convert the moles of KOH into the molarity of KOH. To do that, we have to take the 45 milliliters of KOH given to us in the problem. If we divide 45 milliliters by 1,000, we get 0.0450 liters. Unfortunately, there's a mistake in the problem here, and the unit next to that is milliliters when it should be liters. Finally, we take the 0.0150 moles and divide them by the 0.0450 liters. Again, it's supposed to say liters there, which gives us a molarity for the KOH of 0.333 molar. There's an alternative way we can solve this problem. That's why it says or there. We can also use an equation that comes from the dilution equation. Here we have that Ca times Mb times Vb equals Cb times Ma times Va. The C stands for coefficient, the M stands for molarity, the V stands for volume. The little a stands for the acid, and the little b stands for base. As you can see, that it's the coefficient of the acid times the molarity of the base times the volume of the base equals the coefficient of the base times the molarity of the acid times the volume of the acid. This can be a little bit confusing. It's very easy to put all the little a's on one side and all the little b's on another side. So just be careful with that. In this problem, we're looking for the molarity of the base. Therefore, we need to rearrange and solve this equation for Mb. In doing that, we divide both sides of the equation by CaVb. And we have that Mb equals CbMaVa divided by CaVb. Next, we substitute the numbers in. The coefficient of the base from the balanced equation is 1. So we have 1 times the molarity of the acid, which is 0.500 molar, times the volume of the acid, which is 30 milliliters, divided by 1, which is the coefficient of the acid from the balanced equation, times the volume of the base, 45 milliliters. When we divide all those numbers out, we get that the molarity of the base is equal to 0.333 molar KOH. And as you can see, we got the same answer as the way we did it above.
Now that we've completed the problem, I want you to think about, again, which technique do you think you'll feel more comfortable with? The stoichiometry technique might take longer, but it's very similar to things that we've done in the past. And if you're a creature of habit, then using the stoichiometry technique will be good because it's the same technique that we've used all year long. The other technique, the equation, might be easier and quicker, but you do need to be careful with the equation because of the complexity of where the coefficient goes. Again, notice that it's the coefficient of the acid that goes with the molarity of the base and the volume of the base, and the coefficient of the base goes with the molarity of the acid and the volume of the acid. Just keep that in mind. In this second titration problem, we're only going to use the equation technique. But I want you to pay close attention to the balanced neutralization equation. The coefficients in this one are a little bit more complicated. It's not a one-to-one ratio between the acid and the base. And this is what might cause a problem using the equation when the coefficient of the acid goes with the quantities for the base and the coefficient of the base goes with the quantities of the acid. Keep this in mind before we start the problem.
What is the molar concentration of 50 milliliters of barium hydroxide, BaOH2, that is completely neutralized by 15 milliliters of 0.003 molar HCl during a titration? In this problem, it's nice again to find out which one is the titrant and which one is the analyte. Again, the analyte is the substance of unknown concentration, which in this case is the base, barium hydroxide, and the titrant is the substance of known concentration, which in this case is the hydrochloric acid. The next thing we should do, as you should do with all titration problems, is balance the neutralization equation that goes along with the problem. In this case, the balanced equation is 2HCl plus BaOH2 yields BaCl2 and 2H2O. It takes twice as much hydrochloric acid as it does barium hydroxide to neutralize. In this problem, we're going to go straight to using the equation method because I think it's a little bit faster. Again, the equation is the coefficient of the acid times the molarity of the base times the volume of the base equals the coefficient of the base times the molarity of the acid times the volume of the acid. In this problem, we're solving for the molarity of the base, the unknown concentration. Therefore, when we rearrange the equation, we get that the molarity of the base equals the coefficient of the base times the molarity of the acid times the volume of the acid divided by the coefficient of the acid times the volume of the base. The next thing we need to do is substitute our numbers. In this case, the coefficient of the base is only 1, which came from the balanced neutralization equation. So we have 1 times the molarity of the acid, which is 0.0030 molar, times the volume of the acid, which is 15 milliliters, divided by 2, which is the coefficient of the acid from the balanced neutralization equation, times the volume of the acid, 50 milliliters. When we divide that out, we get that the molarity of the base is equal to 4.6 times 10 to the negative fourth molar.
Now that we've completed the problem, did you pay close attention to the coefficients? Do you think you'd be able to repeat what we did here?